appreciate it though if at some point in time, I'm going to make you put them away in a minute, but at some point in time, if you would actually look over your lab reports. I actually took a lot of time making comments all over them, and I realized you don't have to turn them in again. And so I just hope you read the comments so that you can get better at writing lab reports. So please, as a favor to me later, not during class, read the comments for the lab reports. Okay? If you have any questions about the homework, feel free to come by. I have not posted a key to our practice exam, but I will be, so that we can practice that. I will be around tomorrow. I have organic lab at 12:50, and then inorganic presentation, of course, in the morning at 9:30. But otherwise, I should be in my office at normal hours. On Friday morning, I will also be around. So if you have questions prior to the exam. Okay, put it all away. Don't have to read it anymore. Just right now.
I'm just so confused as to what everything means.
I know, I started. But I knew I'd forget because I had half of things the other day. And at least you didn't get what's
No. You okay? No. Why? I had a business test today. Did I explain anything?
Today we are going to talk about organometallics, a specific type of coordination compound. So here's my disclaimer for the day. I get really excited about organometallics. I think it sucks that I have to spend only one day talking about organometallics. It is my subject of my PhD. It is what I do research on. I could write a whole class on organometallics and have tons of fun with it, and you guys would have fun with it too. But we're going to stick to the basics today. There's some of those lies that from the beginning of the semester that are hidden in this organometallics section. How many bonds carbon can have, whether carbon can be bonded to metals, things like that, that are hidden in here. But mostly I want you to be able to recognize organometallic compounds. So that's our one goal, recognize. Then I want you to know whether they're stable. Okay? And to figure out whether they're stable, we're going to do electron counting.
It's almost as fun as
Just a collective group. Oops, that's 3.
I wrote 3 too. It's okay.
Glad you're sticking right with me there. In order to do this electron counting, we have to know something about ligands. So I'm going to put that under this. Okay, and the organic ligands in particular, since we already know our inorganic ligands, like the phosphines and then amines, all of those. And then I want to show you an example of organometallic catalysis, because that's where a lot of the fun is that they're interesting complexes because they make things that were unreactive more reactive. So if we're going to be able to recognize organometallics, we better define what they are. What do you think they are?
Organic molecules with metals.
No, metals and organic ligands.
Metals and organic ligands.
Organic ligands.
have carbon bonds. So that can be that it's actually a metal with the CH3. And you saw some of those examples in organic. Where we had Grignard reagents and lithium cuprates. Those are very nice, simple ones that have just a carbon on there, an alkyl group. This makes a big delta minus, something that's not usually on a carbon. Usually, we put an electron group, we make it a carbon plus. We also can have carbonyls. And we know that these were also considered in coordination compounds. So sometimes if it's only got carbonyls, it's a question whether it's an organometallic. Because carbonyls don't act like other metal carbon bonds. So these definitely fit in the organometallic category. These maybe fit. Cyano groups don't fit. So even though we said that it was metals with carbon bonds, there's kind of a few exceptions. Carbonyls being kind of on the fence, and cyano groups being more, they're not considered organometallic. If we pull off the cyano, we have that negative charge on the carbon, and that carbon-nitrogen bond is really short. So in a lot of ways, it's equivalent to a halogen, I minus or Cl minus. And so when we're looking at chemistry of organometallics, the reason why we don't consider cyanos in the organometallic class often is because they basically act like metal halides. So that's why they get dropped off. So this one is organometallic. That one's a maybe, and this one is not. Well, there has to be more examples than our simple little alkyl if it's an entire field and it's worthy of too many years of study, personally. So let's talk about some of those ligands. And I want you to make a table, so I want you to leave room next to this list of ligands. Because we're going to create a list of ligands, and then we're going to come back and do charges and electron counts. So, this ligand, what is it? Cyclopentadienyl. Ferrocene was on your quiz. Ferrocene was one of the first compounds that was reported to have a metal carbon bond. It's a really cool sandwich structure. It has a cyclopentadiene, and the metal in the middle. And there's lots of different metals that can go in the middle, and it just bends those cyclopentadienes whether it has to fit in the ligand or not. Okay? So they're really popular. We write them like this, and really by itself it has a negative charge. What you're really saying is that there are double bonds, a lone pair, which makes a negative charge on this 5-membered ring. When we bond it to a metal, we often get lazy and say that the whole thing is bonded through the center. What we're trying to say is that we are donating all the electrons that are in the aromatic to the metal. So anything that was in a p orbital is being donated to the metal. So another way you can write this, and actually if you're looking at these structures on SciFinder, they force you to write it in this crazy way, which makes it hard to draw. But you draw the 5-membered ring, and it's actually bonded to all 5. Do you remember what, from kind of reading the table, what that would be called? It's the hapticity. So we're going to put this over here. Number of connections. Which is represented by eta and then a number. So what I've drawn up here for you is actually eta 5 cyclopentadiene, which is abbreviated CP. So that's what it was, yes. If it's only bonded through part of it, we can have that double bond not interacting with the metal, but the other 3 carbons donating to the metal. And we would still say that it's a cyclopentadiene, but we would say it's an eta 3 cyclopentadiene. Can we have even less? What would an eta 1 look like?
Just one bond chilling.
Yeah, just the lone pair is interacting with the metal. Like I said, I wanted you to leave room, so hopefully you did. Now we're going to create a charge and the electron count. I should warn you, there's 2 different ways to do this. One the Brits use, one we use. And so you'll find different things in different books. We're only going to do one method. It's the ionic method, or the ion donors. So when we make this up, both systems come to the same electron counts, but they just do it in different ways. So for any ligand, to figure out the charge, what you're going to do is draw it all by itself. What would it be like if it was on its own? And so we're going to look at this part of the kind of table that we're making. What's the charge on this molecule? -1. Because we have the lone pair with a negative charge, or we said it was an aromatic with a negative charge. Those are equal structures. How many electrons does it have that are being donated to the metal if it is eta 5? 6. Because all of the electrons in the aromatic system are being donated to the metal. So we're donating these 2 electrons, and those electrons. Okay? There's 6 electrons spread over 5 bonds to carbon. Yes, that's all crazy, but that's kind of how we're counting the electrons. It's a pi interaction. So what would the charge be on an eta 3 cyclopentadiene?
It's still -1.
It's still -1 because you always come back to what would happen if I took the ligand off. What would its charge be if I took it off? Then to electron count, it does change because these are the electrons that are being donated to the metal. So the electron count would be 4 and 2. Questions on that? Yeah.
Could you just briefly explain where you got the 4 from? Is it because there's 2 that are not participating in bonding? Or
Yes, so if we said that we took this off, it'd be a negative charge, which is 2 electrons, and the double bond.
okay.
And then these 2 electrons are not participating, so it's a donation of 4. Just like this one, if we took it off, it'd be a negative charge on that carbon. That's why it's donating 2 electrons, even though it's only through 1 atom. So, if we look at another metal bonded system, do you recognize that one?
Allele.
Allele. What is the allele when we take it off? I wasn't real strict on this on our quiz. But it's a negative charge on the carbon, right? It has a resonance form. Just like up there, we get a resonance form for cyclopentadiene. And so our hybrid has negative charges kind of on the outside carbons. It has this dashed line. That's why we draw a picture that has the curve, right? Because those electrons are spread out over all 3 carbon atoms. When they're bonded to a metal, they take all of the electrons in that and they donate it to the metal. So what would our charge be? Oh wait, first what is our eta here? Eta 3. So we could also draw this as a metal bonded to 3 carbons like that. If you drop bonded to 3 carbons, you get rid of the double bond because you're showing the electrons in a different way. So eta 3, allo. Okay. So charge? Negative 1. So if we go back there, it had a negative charge, which is 2 electrons. How many electrons is it going to donate then?
4.
4 electrons. Can we make it eta 1 allele? Yes, it's going to have a 2 electron donor, a -1 charge, and what does it look like?
It's just bonded through the negative carbon.
Yeah, so it's just bonded through 1. So we've got this double bond kind of sticking off the side. Here's our 3 carbon. Let's keep going with more ligands. Let's see. What's this one?
Benzene.
Benzene. And one of the oopses on the quiz was that there was a benzene in one of those structures, but in order for it to be an organometallic benzene ligand or an organic ligand, that benzene has to be directly attached to the metal. Okay? We're mostly concerned about what's directly attached to the metal. So we can write it this way. We could also write it with the metal with the 6-membered ring, and it hooked to all of them. Which looks like this. Now, is benzene charged? No, so when we get to the column of charge, it's got a 0 charge. And its electron count is 6. Because if we go back draw benzene without its resonance. We have triple bonds. This is always a hard one for me to draw. My body does not want to draw an 8-membered ring. Okay?
1,5-cyclooctadiene.
1,5-cyclooctadiene. It's just COD. Okay. What do you suppose? We didn't include the hapticity here. This was 8-6. We could have 8 or less on the benzene. What do you suppose the hapticity would be, or the maximum hapticity would be on COD? 8-4. So if we have an 8-4, then our metal is bonded it bends around, it makes a little dome. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Okay? So it bends around because it's got the flexibility in these carbons to do so. And so it kind of makes a dome over the structure. And we're drawing this to the double bond. If we want to draw it just to the atoms, if we draw it to the atoms, then we'd have 2 over there, and 2 over here, and then our bridge in the middle. So we could have a hapticity of 4, so it leaves 2 of the electrons out. We could have a hapticity of 2, or at least leaves 4 of the electrons out. Most of the time, though, because of the strong aromaticity of benzene, it's going to be 86.
Why is the max 4?
Because on all of these rings, we're not going to break any of the sigma bonds. All that's happening is the electrons that are in the double bond are being donated to the metal. So that's why when we get over here to the electron count, it's going to be 4. It's giving 2 electrons from each of the pi bonds. We'll see some examples where the carbon is directly attached to the metal with a sigma bond, but all of these so far are pi bonded ligands. So what's the charge on that?
0.
0. There's quite a few, but I think of these cyclic things, but I think one more example and we'll have killed it. So, what is this one?
Cyclobutadiene.
Cyclobutadiene. And so, we can say a square with a little circle in it. Cyclobutadiene, is it stable as an organic molecule?
No.
No. You'll remember it's actually anti-aromatic. But when it's coordinated to the metal, because of the back and forth transfer of electrons, it actually can be stable. So you can stabilize an anti-aromatic molecule by putting metal on. So we've drawn metal. Little box above it, bonded to all the carbons. 8-4. Charge 0, 4 electrons. Questions on that one?
What would be the shorthand for cyclobutadiene?
I don't know that one off the top of my head. Let's see if it says. No. I don't know. No. I don't know.
If I don't know, definitely don't know.
Okay, so a lot of those are using the pi electron. electron. Let's look at a couple that are sigma bonded. So, I'm loving having colors. This is fun. Let's go back to the one that we had right at the beginning of today. What is this one?
A methyl group?
An alkyl. Okay, because that's an alkane that we're putting on there. Kind of. What would happen if we took off CH3? Is CH3 stable by itself?
No.
Would it be charged?
Yes.
Yeah, it looks a little funky, but we'd make a CH3 minus. Right? Because that way we could fill the octet. So when we get to our charge and electron count, what is the charge? -1. What's the electron count? 2. Question? Now those don't have to be H's, they can be R's. It's mostly that it's how it's bonded to the metal. And so we have a double bond. What is that called? A carbene. Right? A carbon with a double bond, a carbene. And that was the other one on the quiz. It had an R group off there. That's carbene. So how would we write a carbene by itself?
Really angry color.
Something really silly looking. This is where we see some problems with the method we're using for electron counts. Because that is not a real molecule. But that's what we're going to call that ligand. Oh my God. It's never going to exist like this, but at least then it would consistently follow rules. So our charge would be -2. What's the electron count then?
4.
4, because it's giving all of those lone pairs. So what do you think this one is?
Carbine.
Carbine. So what would be the 3 minus? No, really, it doesn't exist like that, but we're going to pretend.
Just go with it.
And so how many electrons are being donated? 6. Now, often, organometallic ligands are also in with regular ligands, right? So aqua ligands or chloride ligands. So just for good practice, we're going to put some regular ligands up here. So what if we have a metal halide? What would the charge be? Well, usually the halide exists as a negative charge, chloride or so. So we would have a -1 as the charge, and how many electrons does it donate? 2. How about our metal NH3? How does NH3 exist in the world?
Happy NH3.
Just NH3 with a lone pair. So, charge is 0, count is 2. Aqua complexes, or aquo complexes, with water on there. Water exists as water. Imagine that. 0 and 2.
So everything else is on the opposite of that.
And everything else that had more than one lone pair was donating all of the electrons from all of the lone pairs.
hydrogenation, but it's not at the end with the halogens where it's most likely. So we would just usually, these are considered sigma bonds. We're drawing them as sigma bonds, so we only have these two. So a hydroxide, what would a hydroxide be? It's a minus charge, but it only gives 2 electrons because we're only thinking about the sigma bond unless we draw them. So now that we know about ligands, we actually have to put this to counting on our metal. So the steps. Thing that you have to do is you have to figure out the charge on the ligand. And the reason why you have to do that first is you have to then come up with the oxidation state of the metal based on the overall charge of the complex. So if we know, we'll have to do an example to actually see this. So let's make the rules first. So first, determine the charge from the ligands. Then you have to determine the oxidation state of the metal. Easy steps. Places we can go wrong, but 4 easy steps. So charge on the ligands, oxidation state of the metal, electron count, and electron count on the metal, and then you add it all up. And there's some nice things that come out. 18 electron organometallic complexes are stable. Why would 18 electrons be stable?
3 shells filled.
All the shells are filled through a noble gas flow. So particularly for an octahedral complex, an 18 electron thing is great. 16 electrons for a square planar are also very stable. Let's think about some of the complexes that we have seen. And we're just going to put just regular old ligands here. So I'm not using the organic ones right now. We can use this electron counting system for the coordination complexes too. So the chlorines are negatively charged, the amines are neutral, so that means we have a platinum 2 plus. We have, so how many d electrons is a platinum 2 plus?
8.
D8. And then we have 2 Cl minuses, so that's 2 times 2. So 4 electrons coming from the chlorine. And then we have 2 NH3s, so we have 2 times 2. 4 electrons coming from the amines. 8 and 8. 16 electrons. And so there's a very good relationship between a D8 metal and the square planar based on this electron count. Well, so let's throw in some things that are organic, and we'll go through them. And I'm going to leave this up here, so I'm just going to move around. Hope that's okay. often, to do this process, I actually write out what my ligands are. I have a CH2, CH3. How would that exist out in the world as a negative charge? So that means charge-wise, it's going to be a -1. Electron count-wise, it's going to be 2. And then I'm going to add this column as total electron count so that I can multiply by a number if I have more than one of the same ligands. But I only have one of that, so we have total electron count of 2. Now I have a bromine on there. That also is a negative charge. This bromine exists as bromide. So it's a charge of -1, an electron count of 2. There's only one of those, so we have a total electron count of 2. Cyclopentadiene exists as a negative charge. Okay, that was our first one up there. So it's going to have a charge of -1. And I have 2 of them, so overall it's contributing a -2 to the structure. How many does each cyclopentadiene contribute in electron count?
6. That one.
6. So how many electrons do we have? 12. Okay. This is looking scary, kind of, if we're trying to get to nice stable complexes. Because how many electrons have we used? 16. Okay, so what is the oxidation state on our titanium? It has to, if this overall complex has no charge, and we have 4 negatives, then it has to be 4 plus. And if it's 4 plus, how many electrons is it contributing? 0. So our titanium 4 plus gives absolutely 0 electrons. We end up with a 16 electron complex. It might be stable, but it would probably react to get one more ligand. So 18. Okay. Do another example, and we can come back to this one if you have more questions after you see another one. Okay. Let's start with the easy ones. We have carbonyls. Carbonyls have those counts. 2. And charged.
-1.
It is not. This is a plus and minus. So overall, it's a neutral molecule. So it's going to have a 0 charge, and it's going to be a 2 electron donor. And we have the total electron count. Since we have 2 of those, that's going to contribute 4 electrons. Our phosphines. Doesn't really matter what R is. What matters is that the phosphine is coordinated to the metal. Phosphines are like amines. They have a lone pair, no charge. So they're a 0 and a 2. And there are 2 of those, so an electron count of 4. Our next ligand is our CH3 alkyl ligand. So it's a sigma donor. Charge is -1. How many electrons is it donating? 2. And we have one of those, so total electron count of 2. The allyl, or not the allyl, the alkenyl. So it's an alkene. It's a double bond. Which category does this fall under? A sigma or a pi?
Pi.
right to the middle, just like up there, we kind of drew things to the middle of something. It was a pi donor. So this is a pi donor. Alkene has no charge, but it's donating the 2 electrons in the pi bond. So it's a 2 electron donor. It's a 2 electron times 2. And we get to our rhenium. What's our rhenium charge?
+1.
+1. So how many d electrons is that?
6. No. Still 6.
D6. We have 18 electrons. It is stable. It also means if it's going to react, it's going to have to lose a ligand. Do a dissociation. That would be consistent with an octahedral coordination complex. Questions on either of those? How we did it? Okay, I'm going to put 2 more up there on the board, and I want you to work through it.
When we're looking at the CP molecules and how it's bound to the metal, how do we decide how many electrons that's actually donating to the bonds? They can have 5, they can have 6,
Right.
4, or 2.
So if it is just written as CP, or if any ligand is abbreviated, it's going to be its highest hapticity.
Okay.
So if you see a benzene and it's not specified that it's only A to 1, it's, or if it's not specified A to 2, it's the A to 6. So we assume the hapticity is the highest one. Because that's what it wants to do, kind of like bidentate ligands are easier to put on. It's easier to take all of the electron density from one of these sandwich compounds.
Wednesday and Monday. So
Okay.
where did you want to find it out?
That.
Where did you?
So for each one of these, there's one piece that's new. We want to get the examples that are multiple. the new piece on this one? That it overall has a negative charge. So when you're figuring out, you've got a Cl minus and a CH3 that are minus, and then two neutral ligands. So we have two negative charges. Overall charge is one negative, so our rhodium is plus. What's the new one on this one? The H. H is all by itself. It's going to come off as H minus. A hydride, right? Because we talked about metal hydrides, borohydride, all the metal hydrides is a negative charge. So the charge is -1, the electron count that it gives is 2. Over there, the molybdenum has a positive charge. That's the only thing that's new on that one. And then the one that has the triple bond, how do you suppose we deal with metal-metal bonds? So far, we've split them based on kind of ions. Cut it right down the middle. Cut it right down the middle. 3 electrons go to one, 3 electrons go to the other. So that the rest of this molecule is going to donate 3 electrons and no charge. Kind of like if we say HH can be broken up into different things. It can either become H plus and H minus, and then we have to worry about the charge. Or it becomes H dot and H dot. Right? And like they split up in radicals. There's no charges on the radicals. That's what we're doing up here. We're just saying that there's 3 electrons that are being left behind. This one happens to be symmetric, so the electron count on either molybdenum will be the same. You can chat with the person next to you, figure out if you agree on how these electrons come out.
I'm having problems with the scary phenomenon. With the scary phenomenon? That one I haven't done. Did you get that one? I haven't done that one. Then I'll work on the phenomenon. Let's switch these. So vanilla. So these would just be carbon bonds. So this alkene. So that would be divided in half. So it's 3 ammo bond. And then so it would be 3, 0, 3, 3. Whatever, I'll do that. Okay, and then on that one we have a -1 charge times 3, which would then be and then that'd be doing 2, and I have 3 of those, so it's 6. Oh no, I don't like -3. Okay. Yeah, see. So it's a -3 on molybdenum, which is still nowhere near enough electrons. So put me at 3. And I get 12. I got 18 for the second one.
How'd you get 18? It's fast. I don't know, I can't figure it out. I get 12. What did you wrong? Why did you get 12?
Because I did something wrong. What did I count wrong? Did you forget to multiply that there's 2? There you go.
No, wait, 2 what?
There's one there and there's one there, so there's 2 current meals.
Yeah, 2, which is equal to 4.
Oh, okay.
I got that.
Then your
Why do you only have, is more than 4 plus?
yeah,
Where's that second negative?
because there's 2 from there, 1 from there, and it has a positive charge, so
So
it has to be
negative
4
2.
plus.
Ah,
There you go, bud.
I knew there was a step I hit. So it'd be 2, which would put you at the right number of 18. Okay.
Yeah, and then the second
So
one,
the
I'm
second
getting
one
something gross like that
is
too.
just an alkene, right?